So today we're going into what's called normal distributions and what happened to the screen. Oh, I apologize here. That came unplugged. There you go. So we talked about density curves a couple of days ago, and we had some rules for density curves. And density curves were always touching or above the x-axis. And we want that because we're insisting that the area under the curve be equal to 1. And if we go below the x-axis, then we start subtracting areas out. So we want to keep it all clean. We'll have all positive numbers so that area above the curve makes sense. So we'll be using several density curves that in this course of statistics that are used by statisticians a lot. And the one we'll spend the most time with here at the beginning is called the normal density curve. So what color am I writing in? Okay. Okay. So the normal density curve, unlike the ones that we saw on Monday, doesn't have straight sides. And, well, that looked bad. And it goes forever in the negative and positive direction. It is always above the x-axis. It doesn't touch the x-axis. And looks a bit like, okay, so kind of badly done, but looks like a snake that ate a rat. I don't know. Okay. You know how when a snake eats something big, their middle gets kind of big? Okay. So, some people refer to this as the bell curve. We're going to call this the normal density curve. It is symmetric. It is, as I said, always above the x-axis. And the area under this curve from negative infinity to positive infinity, because this curve goes from negative infinity to positive infinity. So the area under the curve from negative infinity to positive infinity is equal to 1. It's a density curve. Okay, so that means, out of screen here, that this area that is not even, that doesn't ever stop, all this area through here, when you add it all together, no, it doesn't ever touch the x-axis. It's always above the x-axis. So it doesn't touch. So it's one of those things that's going to be real hard to find areas under this curve since we can't do it geometrically. And for my calculus and post-calculus students, how do you find areas under a curve? You integrate. So the equation of this line, and I have to look it up because this year, since I'm not doing a graduate level stats class, I don't have it in my head. I'll find the equation here in just a second, or I'll look it up online. Here we go. So the function that defines the black line, the actual curve, is 1 divided by, now this equation has what's called parameters. And the parameters are standard deviation, abbreviated by a lowercase sigma. Yeah, so I start here, I make a little circle around, then make the tail. Times the square root of 2 pi times, and you'll love this part, times e to the negative 1/2 x minus the mean divided by that sigma number, all of that squared. This is the equation. So I'll get there. I'll write down my definitions here in just a second. Oops, f of x equals, sorry. No, you don't have to memorize this. All right, so f of x, we understand f of x, hopefully.
Wait, is it e multiplied or under?
Oh, sorry, it's times e, so it's above the fraction line. Okay. So, shh. So this is a really complicated function. We use it every day, but if you've taken calculus, you know that you don't have to do integrals by hand, because what will do integrals for you, especially if you have definite integrals? Your calculator will give us this function. So we don't have to be sitting here working with this hard equation all the time. Okay. So this long, ugly equation represents just the line part. Okay? Just the curve part, not really a line, it's a curve. All right. The necessary parts in this function are the standard deviation and we've in the past been abbreviating that S, but we're going to abbreviate that with this lowercase sigma. I'll write it again, because it's going to be the standard deviation of a whole population of data and not a small sample of data. Pi, we should know what pi is by now. E, what's E approximately? 2.784, is that a good approximation? So that's some number, but it's an irrational number, goes on forever, abbreviated by the letter E. Okay. Here's my variable. My x is going to be values along the horizontal axis. And this mu is, so I'm going to write out this, you call this mu. And this is going to be our abbreviation for the mean of a whole population of data. And I'll write that out one more time. It's a U where the left-hand tail is really long. Okay? Oh, that's right, using physics. Mu's used a lot in science. You know how to write one of those. X is my only variable in here, and X are going to be these values across the horizontal axis. The M is mu. It's a mean for a bunch of data. The sigma is the standard deviation for a bunch of data. There's no u, it's a mu. Lauren, possible to stop? Thanks. Okay, here we go. So this is this crazy curve that we're going to be talking about a lot. Now this crazy curve, if I want to find the area under this curve, I would integrate this. We won't integrate it. We will let our calculators integrate it. Am I going to have to enter this crazy formula every time I put it in my calculator? No, because it's used so often that the integrals are right there in, calculated by the calculator with a single button push. And there are, before the advent of calculators, there were strictly tables to do this integral. And so there's tables all over the place of standard normal distributions. But this one, so this one will have a lot of freedom to use our calculators on. Okay, so some of the other qualities of this distribution. It is this distribution, if you saw a histogram, would start looking like this. Okay, and if you had a big enough population, you would keep going, getting smaller and smaller out to the left and right. And if you have just tons and tons and tons of data, all these bars are going to start kind of melting into something that averages out to be a normal distribution. Okay, so you can think of all the green that's under this curve as being a whole bunch of bars in a histogram, in a frequency distribution. Okay, now these bars, they're not going to be numbers, because if they are, they're not going to be whole numbers. They're not going to be counts, because if I start adding up counts, I'm going to get a number bigger than 1. So these bars are all going to be in percentages. So these bars are all percentages, and when you add up the total of all these bars, has to add to 1. So they're going to have to be proportions, percentages, in order to make this work. Okay? Now, some other qualities of this distribution, besides it kind of looking like that, and I'll keep making more of these, is that, and they don't all look real good, sorry. Here's my center of this distribution at the highest peak, and this point is the mean of all the values across the x-axis, of all the values with their frequencies. Okay, so you might have, your mean might be 100, and you've got a bunch of values this way and a bunch of values this way, and 100 will happen 33% of the time, and 101 will happen 27% of the time, and you'll be able to figure out a mean of all of those values across the x-axis and their proportions. That mean is going to be right there at the center, at the high, to represent the high peak of this distribution.
Does that say mean of all values?
Mean of all values with their frequencies across the x-axis. Now, this function that represents this normal distribution, this normal curve, has what are called inflection points. What's an inflection point, those of you who have taken calculus? Second derivatives equal, no, second derivatives 0. Okay, the point where the second derivative is 0. Okay. So when I ask calculus students, I'm obviously saying something that not everybody needs to know, but they do. The inflection points are, I look at this curve and it's kind of going down and then it's kind of rising back up. The inflection point is right over here and over here. And this point of inflection is the mean of the distribution plus one standard deviation. Okay, so I could calculate a standard deviation for all these bars. You know, I put all these bars together up here, and I can calculate a mean. I can calculate a standard deviation. If I take that mean and I add that value, one standard deviation to it, and I go out here on my x-axis here, when I look up here, that's the inflection point to the right of the mean. That's the positive inflection point. And the other inflection point is the mean of the distribution minus one standard deviation. Okay. All right, so let's say I have a bunch of data on one thing that if you put every woman's height into a list and graphed it, you would get a normal, approximately normal distribution, because a full normal distribution is all theory and not, not reality. You would get a normal distribution, and I believe 5 foot, if you put young women's heights, I think the average woman's height is 5'4". I don't want to write 5'4" on my graph. How many inches is 5 feet 4 inches? 64. Okay. Okay. And if you put all of those heights together and you calculate their mean, it gets to be 64. You put every woman's height together and you calculate the standard deviation from all those values. I believe you get a standard deviation of 2. Two inches. Okay? So when I look at my little distribution here, I go out to this kind of looking inflection point, if you can see it fine. It's kind of starting to go down and starting to go back up. And the mean plus one standard deviation would be how many inches? Now I'll go back one standard deviation to 62. Now, the mean plus 2 standard deviations would be, add another 2. The mean plus 3 standard deviations would be, the mean minus, there's minus 1 standard deviation. The mean minus 2 standard deviations would put me at 60. The mean minus 3 standard deviations puts me at 58. We tend not to go more than 3 standard deviations. Now, if I'm really in a normal distribution, the area under this curve from the mean minus 1 standard deviation to the mean plus 1 standard deviation. So I'm going to color that in green. This area under the curve is 0.68. Because if I integrated this equation and I did a definite integral from 62 to 66 from plus and minus 1 standard deviation, 2 inches, being under this curve, using that formula that I gave you for it, you'll get 0.68 for the area approximately. That comes from the formula. Okay, but we're not going to integrate it. Like, why should we? It's been done a million times. You know, we don't need to be doing that kind of math on it. Okay. If I'm on the same curve, to 60, 58, same curve, and I go out 2 standard deviations, so I'm going to call this plus and minus 2 sigmas, and I look at all that area between 60 and 68, this area is 0.95. And somebody said, what does this signify? I'm going to get to what this really means to you in just a second here. And if I go out from the center three standard deviations, I go 1, 2, 3 to 70. Start at the center, 1, 2, 3 backwards to 58. That area under that curve is 0.997. And these numbers are approximate. We'll get exact here a little later. Okay, so what does this mean? Go back to the meaning of the very first graph, and I'll go back down to that one in just a second. These are women's heights whose average are 64 with a standard deviation of 2 inches. That 0.68 means that 68% of women are between what heights? Okay. When I go out 2 standard deviations, I'm talking about the mean minus 2, minus 2, minus 4. So I'm talking between 60 and mean plus 2 standard deviations, 66, 68. What percentage of women are between 60 inches, 5 foot tall, and 68 inches, 5 foot 8? 95%. And what percent of women are between, now we got 58 to 70 inches. 58 is 4 foot 10. 70 inches is 5'10". What percent of women lie in that, meet that category? Okay. So that's essentially All women fall in there. We know there are women that are shorter. We know there are women that are taller. Okay? But so that's where that 0.3% comes in. And that's what this is signifying. Oh, yeah. So I'm almost at 1 now, aren't I? I've just got a little bit left in the tails, 0.3%. In many cases that is, and we're gonna decide what's close enough to 1 here as we go through the semester. But for what we're doing right now, sure, that should be essentially 100%. Okay. Oh, we're good on time. I'm gonna go a little bit longer here. All right, so this is going to be a talk and turn kind of an assignment. There's my center. I'll use these same numbers. Write these down on your paper because you're going to do a little math here for me. I'm going to start you off between 62 and 66 inches is 68% of this area under the curve. From 62 to 60 would be 34. 34%. Okay? Do you think you can fill in the other? It's actually 6 blanks. Can you fill in these two and this one on the end that goes to infinity, and these two and this one on the other end that goes to infinity? You're going to need to do a slight bit of arithmetic. Arithmetic. Decimal arithmetic. Okay, did you figure it out? No? Doesn't matter because it won't be wrong.
Yeah, probably was.
I probably want to watch the movie if you told me.
Oh nine, oh nine, oh.
Got it. He's got it. Mark's got it. All right, come on. What goes in this little space between the 60 and the 62? .125, do we agree? 0.135. I agree with that. How did you get that?
I did 0.95 minus 0.68 divided by 2.
So that's 0.27. Divide that by 2 and got 0.135. Okay? So the next piece was a little bit harder arithmetic. So how about the little piece between 58 and 60? .025? 0.0235? 35 or 45? Come on. You got a calculator out.
0.025.
0.025? Yeah.
So the furthest we're going to go is 3 standard deviations.
Yeah. Yeah, generally, yeah. 0.02 what? 35? Okay. Now, how much is left in these outside? They're called tails. So it's 0.997 to go from 58 to 60. So subtract that from 1 divided by 2 to get what goes in the outsides here. 0.0015. Okay. So what percent of females are between 64 and 68 inches tall? So you add 0.34 plus 0.135 and you get 475.
So when it's plus or minus 1 standard deviation,
Mhm.
is it always 0.68?
Yeah, it's approximately, but yeah, use that. They call that the 6895 99.7 rule, but it's an approximation, but yeah, you can use that. Yeah, you can always use that.
It's always there.
Okay. What percent of women are greater than 5'10"?
What's 5'10"?
5'10", 5 foot is 60 inches. What percent of women are greater than 60 inches? 70 inches. What percent of women are greater than 70 inches? 5'10". 0.15%, yeah. 0.0015 is 0.15%. Okay, so I'm just going to say greater than 70 inches, 0.0015 or 0.15%. Alrighty. What percent of women are less than 62 inches? I need an answer to this question, so get out a calculator if you can't do it in your head. Because I have one more word to define. I'm sorry, that's 16?
Yeah.
Okay. So that's 0.16 or 16%. If you are in the 16th percentile, It means that 16% are shorter than you. It means that 84% of women are taller than you. And what height is the 16th percentile? Where on the x-axis are 16% shorter than you and 84% taller than you? Okay, so 62 inches is the 16th percentile. Alrighty. That was good. Principal up.